Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. We'll be focusing on Module 10, Distribution Network Automation and Restoration Study. We'll be discussing thoroughly distribution network restoration mechanism. Now, restoration is ensuring continuous electricity supply is a key concern post privatization and deregulation of the power sector. That means it is the responsibility of the distribution system owner to make sure there is a continuous electric supply to the consumer. Now, distribution networks, being the final link to end users, must deliver reliable and efficient power. Now, majorly due to their radial topology, faults in the network interrupt power to all downstream customers. That is, because of its radiality, the moment there is a fault, the rest of the consumers are not going to get any electricity access. Now, statistics indicate that most electricity supply outages and originate from the distribution level. Enhancing distribution network resilience is critical to maintain power system continuity. Now, self-healing is an important area where even whatever may be the challenge, the self-healing enables automatic and intelligent restoration of the network during emergencies. Utilizes equipments, algorithms, and communication technology to maintain optimal operation. Now, as you could see, self-healing process in distribution system, we have a normal operation cycle, and then you experience a fault, then localization and isolation, you disconnect, then you restore the service, and then return to initial state, and finally you become normal. So, self-healing process in modern distribution system become an important aspect, and if it is in place, then you can say your distribution system become extremely resilient. Now, over 80% of the faults in distribution lines are single phase to ground faults, and you could see that effectively neutral grounded networks in which faults create a clear short circuit path with high fault currents. Zero sequence overcurrent protection quickly operate to cut off the fault, whereas high impedance faults are hard to detect due to weak fault characteristics. So, what are the solutions for this? Zero sequence inverse time over current protection, and third, harmonic current based detection must play an important role. So, detection based on grounding type, where non-effectively neutral grounded networks, fault current is small, allowing network to operate briefly. Fault detection is difficult due to small zero sequence current. For permanent faults, need to locate and trip faulty feeder quickly. Traveling wave based detection methods are proposed. For temporary fault, fast arc extinguishing technologies are developed, arc suppression systems using high impedance transformers, two-phase current injection using SVG to suppress arcs, active arc suppression via double loop control with inverters injecting, and then zero sequence currents. Now, when you move to post detection action, where after detecting and tripping the faulty feeder, locate the fault precisely, isolate the minimal fault section using switches connected to the faulted part of the network. Now, the restoration process, after isolating the faulty section, upstream areas are restored by closing the feeder output circuit breakers. Downstream areas are restored using service restoration strategies like network reconfiguration or microgrid formation. These procedures are illustrated using a test network of figure 55.1. So, as you could see, we have a zone 1, zone 2, 3 and 4, and finally 5 and 6. Now, the test network indicates there are 6 zones, as you have seen, 1, 2, 3, 4, 5 and 6, and you could see there are faults being created at multiple locations. So the test network indicates 6 zones and a DG unit with black start capability at zone number 6. Okay, so this is we have a DG placed. Now, if a permanent fault occurs in zone 1, that is this section, then switches S1 and S2 are opened to isolate the fault, and zone 2 is restored by closing tie switch TS1, reconfiguring the network topology. Now, during this, key constraint must be respected: power balance, voltage and current limits, radial topology requirements are being maintained. Now, if a fault zone occurs or the fault occurs in zone 5, now in that case DG unit is disconnected initially to avoid operational risk. Switches S5 and S6 are open to isolate zone 5 completely. Since restoration via network reconfiguration is not possible, the DG restarts to supply local loads by forming a microgrid. Now, microgrid formation faces technical challenges like cold load inrush, load pickup surges, voltage and frequency constraint violation. At least one DG must control frequency and voltage. Additional constraint during the formation, that is frequency response rate, spinning reserve, incremental load limit, and finally N1, N-1 security criteria. Now, what are the objectives of service restoration? We need to maximize load restoration with highest priority for critical services, example hospital and government facilities. Minimize restoration time by reducing switching operations. Minimize line losses in the configured network, lowest priority due to short-term use. Now, the nature of problem could be either combinatorial, involving discrete switching decisions, constrained due to technical and operational limits, nonlinear for power flow and dynamic conditions, and finally multi-objective involving trade-off among different goals. Now, classification of approach, we can have either centralized approach or decentralized approach or distributed approach or hierarchical approach. So, focusing on centralized approach for service restoration, it's based on distribution automation system DAS, includes master station, substation, DA devices and a communication system. It operates using global system information, can provide optimized restoration solutions, and requires large scale data transmission from the field, needs a powerful control center CC with high computational capabilities. Risk of single point failure: if CC fails, restoration fails, poses heavy computational burden. Centralized approach are reviewed based on the techniques used for restoration, example, expert system or algorithms. Advantage and disadvantage of each technique are also discussed. Now, expert system based service restoration, as you could see from the figure 55.3, we have knowledge based, database, then inferencing, and finally the solution. Now, in expert system based service restoration, we have different components. They are knowledge base, database, and inference engine. Knowledge base contain domain knowledge as if and then rules. Database stores facts used to match rules. Inference engine links facts and rules and perform reasoning to drive restoration decisions. Now, in case of if and then rules, for example, rule 1, if only one candidate feeder can serve a de-energized zone without violating constraint, leading to assign the zone to that feeder. Now, the rule 2, if multiple feeder are available, then select feeder with the highest operational margin. Rule 3, if any de-energized zone is not restored, then attempt to restore it. What are the advantages of expert system? Capable of providing quick and feasible restoration plan because the rules are already in place. You have to simply fire an output based on the input, and adaptable with a hierarchical or multiple engine design for modularity, and speed, which is adaptable with hierarchical or multi-engine design for modularity and speed. Limitations were difficult and costly to construct and maintain large knowledge bases, does not guarantee optimally or does not guarantee optimality of restoration solutions. Now, the graph theory based service restoration approach, where if you concentrate on abstract graph representation, the distribution network is modeled as a graph where vertices, which normally represent your substations and load zones, edges are representing your switches. The goal is to find a spinning tree radial configuration that satisfies operational constraints. Example, if a fault occurs in zone 1, a new graph that is 55.4, as you could see, is formed after isolation, and a spanning tree is derived by removing one edge from each loop. Now, binary decision tree approach, where the basic idea is to each node represent a switching decision. Binary values, example, x equal to 1 or x1 equal to 1, and the switch closed when x1 equal to 0 implies the switch is open. Paths from root to leaves represent restoration solution, which can quickly generate feasible solutions. Structured representation makes analysis and automation easier, suitable for both network reconfiguration and microgrid formation. Limitations, graph theory based service restoration, where exhaustive search can be computationally intensive for large scale systems. Scalability is a concern due to the high number of possible trees. Now, mathematical programming based approach for service restoration. Mixed integer nonlinear programming, MINLP, offers detailed modeling but is computationally very intensive and non-convex. Mixed integer linear programming, MILP, achieved via linearization techniques for improved computational efficiency. Mixed integer second order cone programming, MISOCP, uses convex relaxation of nonlinear constraint to reduce computation time. Now, the objective function is to minimize either energy production cost, number of de-energized zones, line losses, switching cost, and finally load shedding cost. With different constraints such as power balance voltage current limits, load shedding limits, radial topology, binary switch and zone status. Now, moving to hierarchical approaches which use distributed intelligence to solve restoration problem. Network is divided into subnetworks, each managed by a local agent, and there are majorly two main techniques. One is multi-agent technique known as MAS. Mathematical programming also include hybrid methods combining both of them. Now, in case of MAS approach, that is multi-agent system approach, agents communicate and coordinate based on heuristic rules, capable of autonomous decision making, applied in both network reconfiguration and microgrid formation. Now, whereas mathematical programming approach, in which alternating direction method of multipliers, ADMM, used for distributed optimization. With this note, we conclude the restoration technique in case of distribution systems, and I appreciate for your patient hearing the complete talk thoroughly. Thank you very much. Bye-bye for now.